Okay, we'll specifically talk about roller bearings, which are very ubiquitous, right? So what a bearing involves is basically two rings. Okay, the inner ring, outer ring, and this inner ring obviously goes on a shaft. The outer ring goes on whatever you want to mount it, whatever you want to move, and basically when you spin uh, when you spin the inner shaft, you get isolated movement. You only get movement along the axis along which you have the shaft. So in this case, it will rotate about this axis, right? Okay, so it has inner ring, outer ring, ball or roller. Okay, those are the three main ingredients, and the separator is shown here. This is basically one which basically helps you to uh, basically isolate the bearing one roller from the other roller, and it's just something, a feature which will increase the life of the ball. And of course, if you want to increase the life, you probably want to pay more. So that's the reason why it is not tearing cheap bearings. Okay, now I'm going to. That's not the only way in which you can have. You can also have. You can have. Well, you have two types of bearings actually. You have balls and you have rollers. Okay, so balls are simply spherical lead balls which are used to take in radial forces, and they're not really meant for axial forces. Axial forces are sometimes kind of important. Many applications you'll see that bearings shafts are subjected to both radial as well as axial loads. So these are generally for radial loads. So best example is a bicycle uh, um, bicycle chain that has that element there would have a roller bearing, because you wouldn't have, you see, axial loads there. Uh, the roller bearing is uh, almost a cylinder, and this one is typically used when you want to take in bigger loads, because you get a bigger area over which the force can be transmitted. These also can be used for axial loads. So for example, when you make these along an axis, they actually can take both radial load along the bearing axis and axial loads along the axis of the shaft. Okay, so how do we use, what are the conditions or the criteria for design? The thing which we are most interested in for bearings is something called their bearing life. Okay, so the bearing life is the total number of revolutions or hours at a constant speed of bearing operations under failure. Okay, so it's basically how many cycles will a bearing last before it goes to failure. Now that is a very vague term, because if you have, let's say, 20 bearings, and if 19 fail, then you probably will see that that bearing is no good, because just one bearing working in place, well, it doesn't mean that you can actually use that piece of equipment, because 19 bearings are probably very critical, uh, more critical than uh, the 20th one, right? So in order to resolve this conundrum, what they do is they actually use what is known as the rated life. Instead of looking at, um, they have a number associated with how many bearings can fail, up to which will certify safety or working of the bearing. So it is, the rated life is the total number of revolutions or hours that 90% of group of bearings, okay, 90 bearings will achieve or exceed before failure. All it's saying is that when you're using a part with ball bearings, you will go up to the point where 10% will fail. After the 10% fail, you will basically discard that bearing and use a new one. That's where the 90% comes from. Now, why 90? Why not 80? Why not 70? 90 is just an empirical number. You could, if you think your application requires more stringent measures, you might want to allow only 5% to fail and not 10% to fail. Okay, so what they do in this case is 90% is a good ballpark, and so they use what is known as they call the L10 life or the B10 life, which is basically the same as saying that 90% of the bearings are fine or 10% have failed. So you basically, when you do this tests in your lab and you're trying to ascertain bearing life, you make them move so many revolutions till 10% fail, and then you say, if that whatever bearing bared a million revolutions and 10% fail, then you would say that that's the L10 life is 1,000,000 revolutions. But in another experiment, it so happened that it took only 1,000 revolutions for 10% to fail. Then you say that the L10 life is basically 1,000, right? So that's a measure of the time it takes for 10% of the bearings to fail. That's the rated life, and that's what we're going to use. Now, what we're interested in particular is how does the load carrying capacity affect the life. So it's clear that uh, if you have a bearing which is taking 100-pound force would have a different life compared to a bearing which takes 1,000-pound force. Maybe most probably a bearing which takes 1,000-pound force will fail before uh, a bearing which takes 100-pound force, right? So this is the relation between force F and L. So what they did was they took bearings, they applied it's the same ball bearing, but they took many of these, and then they loaded these the bearing to some force. They cycled them through uh, so many revolutions and waited till 10% failed, and they got one dot here. Then they took the second bearing, put a different force, made it run for so many revolutions, waited till 10% failed, got the second dot, and so on and so forth till they get bunch of dots. Now it turns out that if you make a plot of log f, log of force to log of life, then you get a straight line, which is actually a neat thing, because if it's a straight line, you can actually write the equation of a straight line. So what this is saying is that log f to log L is a straight line. So y equals mx plus c. What is y? Y is log f. What is x? Log L plus c. It turns out that you can actually combine this. You can call this, you can actually write it as uh, f. So I would write this, let's call this tilde, tilde, it is log f. Uh, you know what? You can just write this just to make it very easy. I don't want to involve log. I don't want to involve exponential. So the easiest way is, let's assume that c tilde is log c. Okay, one constant can be replaced with another constant. So if you can do that, then what you can do with this is just following from the rules of logarithms. This m can move up, so L raised to m c. Okay, and once you combine, so log a plus log b is actually log ab, and that's what I use. Log a here is L raised to m times c is same as log m log L plus log c. So you can get rid of logs on both sides. So you get f equals c times L raised to m. It turns out that well, we can just rewrite this as f L raised to minus m equals c. In other words, the product of f times L raised to minus m. Did I do a mistake? I think 1 raised to, should have put 1 raised to m. It doesn't really matter in the end, as you see. So f L raised to minus 1 raised to m is a constant, right? What they do is they write this as fl raised to 1 divided by a. So a is basically minus m equals c. So a equals minus m. Okay, one constant can be replaced with another constant. It doesn't really matter. So the point I'm trying to make is that the product of force times length raised to an exponent 1 raised to a is a constant. Okay, and what they can do is, because they can get these line, uh, what is L? Question. L is the life. F is load. Uh, so because they can get this, and there are dimensions on this, they actually measurements, you can actually compute what A is, because A is basically giving the slope of the line. It's related to M. So they found that A is 3. Here it is. A equals 3 for ball bearing, and A equals 10 divided by 3 for a roller bearing. So 10 divided by 3 is about 3 point, I think 3.333, It's very close to 3. So the formula which you need to remember is that FL L raised to 1 divided by A equals a constant, okay, where F is the load and L is the life. Okay, and life in this case is typically taken in revolutions. Okay, so we'll get to this formula in again. So if this is a constant, what you do is you just write it as follows. If R is used to denote the catalog rating, when I say catalog, it means that when you open a catalog and you see numbers, you'll see this numbers, you'll see FRLR, okay, with our force and life. And then desired load rating is something which you want it to be put in an application. Say you wanted an application where it'll run for 2 times a million, 2 million revolutions, while the catalog rating might be only for 1 million revolutions. So this expression actually tells you how you can, what is the load you can expect for the specimen to take if you choose it from the catalog. So what you'll do is maybe when it is when you use this bearing in an application, you can expect 1 million revolutions at 1,000 pounds force, right? Then if you know that you're going to run this for or you're going to subject it to a force of 2,000 pounds in your application, whatever it is, then it'll tell you how many revolutions will it last. That's what this expression will tell you. I'll come to this particular problem in a better setting, in a problem where you'll be able to understand what exactly is going on here. So this is just a formula which comes from the previous case where it says that F times L raised to 1 divided by A is a constant. Okay, to use it is you just put it for different conditions and you can equate it. So catalog rating, as I said, is the rating which comes from the catalog. This is how bearings are rated. Usually they're rated to 1 million revolutions. So when you open a catalog and say that they say catalog rating, which is a force rating, right, radial load rating, is 100-pound force, that means that that bearing will bear 1 million revolutions before 10% fail. Okay, and that's basically what it is. Now this is just giving you life in revolutions. L is in revs, but sometimes your application you require it to run for hours. So if you think of a turbine shaft running 24 hours per day, that's an easy to crunch number. But if I told you that it ran for 24 million revolutions, you have no clue, because you don't know if it is going to be achieving those many revolutions in 1 month or 1 year and so on. But if I tell you it's 24 hours, you pretty much know what it is. So this is a way in which you can relate revolutions to hours, and there's no real, this is like a simple formula. You just have to get the units right and you can subs one with other. The formula is L equals 60 times N times subscripted S. So I'll call this subscript L so that it's not confusing with L, which is revolutions. In this formula, what you'll see is you'll put revs. Okay, so if you have this in mind, then you can substitute the L in this equation with the subscripted L, and you have a new formula. Basically, it's just a scaling of this formula based on 60 times N. So you also need to know N, which is the revolutions. N is the revs per minute. Okay, so I rewrote it here. Maybe this is a bit, let me get rid of this highlight. So anything you want to know, remember or put it in your formula sheet, this formula and this formula. Okay, so what we'll do is we'll solve a problem. I think that problem will make it very clear what this formula actually is. Okay, so a bearing company rates its ball bearings for 1 million revolutions. Okay, so when it says the company rates, the word is rating. So what I given is essentially the rating. It's 10 raised to 6 revolutions. For a 90% reliability, in other words 10% fail, a desired life of 5,000 hours, So this is a subscripted L because it is in hours, 1725 rev per minute. Desired life of, sorry, 5,000 hours, my bad. This is not what it is. It's saying that's N. N is this, my bad. N, that's desired, right? So it says desired. So desired life. So the subscripted L is 5,000 hours. I shouldn't have put 1725. So 5,000 hours. The number of revolutions is 1725. And you're given a load. So this is the load for everything is desired. So it's all FD. FD 400 lbf. Okay, so in other words, what's going on here is that you're saying is that this is in your application. It could be maybe a bicycle, somewhere in a bicycle. It could be a train. It could be a bus or whatever. This is in your application. You're going to use the bearing for these loads and for this life. This is the one which is your catalogs. This is the company from which you're going to buy the bearing has this rating. It always rates its bearing for 1,000,000 revolutions. So when it says that it can take a certain load, which is unknown, it is for 1,000,000 revolutions. Your goal is to compute the catalog rating. In other words, your goal is to compute FR. This is the catalog rating. And the question is, why do you want to do that? Well, this is what you're told. These are your specs for your application. Based on that, you would compute what is the catalog rating so that you can go and open the catalog and buy that particular bearing which will satisfy your requirement, which are these three things. So what we'll do here is we'll just use the formula FD LD 1 divided by A equals FR LR 1 divided by A. It turns out that LD is given in terms of 60 ND subscript LD 1 divided by A. Okay. So we are talking about ball bearings. So A equals 3. So FD is 460. ND is 1725. LD subscript LD is 5,000. Ball bearing is 3. So we should put 3 there. FR is unknown. LR is 10 raised to 6, 1 divided by 3. Okay, so one equation, one unknown, we can solve for FR, and that comes out to be 3,021, which is, by the way, also known as the C10 rating, right? C10 is 10% of the bearings will fail and 90% will survive. Okay, so what it's saying is, if you want your application to have this bearing specs, it should last for 500 hours at 1725 revolutions per minute with this load. You actually want to choose a bearing which has a load carrying capacity of 3,200. Okay, because you're going to subject it to many more revs over here than what it is supposed to. Okay, so this is how you compute the radial load, the catalog rating, and how you'll use it in your application. Okay. Let's see. Okay. 640. Okay. Let's talk about reliability. Okay. So what is reliability? Well, this is basically it's like a probability of failure. Okay. So when the simplest example I can give you is when you try to machine shafts. Imagine they're going through a procedure where you do grinding and smoothing and so on. and you're trying to come up with shafts of diameter equals to, I don't know, 1 inch, what you will see is that in real world, you will see that if you take 1,000 shafts which come out from the lathe, then you'll see that they will actually follow a distribution which is known as a normal distribution. You'll see that there is a mean of 1 inch, but then there will be some shafts which are less than 1 inch diameter. Some of them are greater than 1 inch diameter, and this distribution actually looks like an exponential, e raised to something. You can check the how the normal distribution looks like in Wikipedia. But the key idea here is that many of the processes in the world are actually modeled as a normal distribution. Another interesting thing is it so happens that if you look at if in many classes when you do the course grade, many times the course grade actually comes out something like this. You'll see that it's somewhere centered around B and C, and then there are some students who have A and some students who fail, and the majority of them sit around B and C. So what you can say from that is that the class follows a normal distribution, and we have seen these things for most phenomenon in the world follows a normal distribution except for a few. Now it turns out that for bearings, they don't really follow this distribution. The distribution is skewed. It's actually known as a Weibull distribution, which has this shape. So in order to get this distribution, what you do is you basically take a bearing to failure, right? I had shown this plot earlier here. So it's a nice fitting plot, right? You can say, do these points actually lie exactly on this line? Well, it turns out that they don't. They actually follow something like this. So when you try to look at the failures, you will see that 4% of the bearings fail within 1/10 of the catalog rating, and then 2/10 and so on. So it's really a distribution which looks like this, and they did these experiments for many bearings, and they found that they actually don't follow the normal distribution. So the area under the curve, so in this case, let's do this. We have 10%. So we talked about 10% failures, right? This is the magic number, 10%. So if you take 10%, let's shade this with yellow. Okay, so what it's saying is that this 90% of the area, this is 9. So the total area under this curve, the dashed line, is actually sums to 1. Okay, that's magnitude of 1. 90% of 0.9 actually over here, and that's where the L10 rating is basically the one which says that 90% of the bearings are safe and 10% have failed. Okay, this just comes out from the doing an experiment. It is not something which you can do numerically. It's a process followed by the bearings. It just happens that they follow this distribution. Okay, now reliability is basically computing the area under the curve, the yellow part, and that is basically a formula which reads as R equals exponential, let me put it with the red. That's a formula you want to probably remember or write down. So you can compute the reliability, which is in this case 90% for most of our catalog rating calculations, based on x0 theta, which will be given to you. It's 63.21 percentile. This is depending on the shape of the Weibull distribution. A shape factor, which is 1.5 for roller bearing, and x0, which will also be, it's the minimum life, which will also be given to you. So you can actually compute the reliability if you knew the life and L10 life. Okay, so this is just telling you, given this reliability, what is the non-dimensional life, or L, or the life of the specimen, and vice versa. If you're given the life, you can compute the reliability. Again, the reliability is important because when looking at failure of bearings, unlike everything we learned in this course, we're looking at percentage failure, or we're looking at some kind of a stochastic distribution. We're not looking at a deterministic number. We don't say pass or fail. We say that 10% of them have failed. So it's a different notion from what we've seen throughout this course. So just bear with me. We're going to come back to this in just a bit. So why we are talking about reliability? So we have looked at 90% reliability. Okay, so the formula we used was that FD LD 1 divided by A equals FR LR 1 divided by A equals F10 L10 1 divided by A, and this is the 90% reliability calculation. That is, when you choose the catalog rating, when you do the calculations for your problem, like in this problem, everything was 90% reliability. Not only you assume that the catalog was based on 90% reliability, you also assume that your application you'll have a 90% reliability. But that's not always the case. Okay, you might say that I don't want to wait till 10% fail. I want to go only till 5% fail. So then the question is how to compute FD LD at say 95% reliability. Okay, how do you do that calculation? So this is what is coming next. We're going to compute the relation between FD and LD at a different reliability. Okay, so in general, if you make a plot of log F to log L, we looked at a straight line, and this was for 90% reliability. Right? This is something we saw right here. This is the plot we got for 90% reliability. Right? What we did was we specified a force, we ran an experiment, we waited till 10% of the bearing failed, we got a dot, and then we repeated for a different load and so on. If you do the same experiment for a different reliability, so let's say that you do it for greater than 90, so you want a 95 or 99, you'll see that you'll get lines like this. So this is greater than 90%, you'll see lines like this. If you do the same plots for a greater amount of failures, so maybe 15%, 20%, 30% of failure, then which means the reliability is less than 90, then you will see that lines will actually be straight lines, very similar to the 90% line, but they will be decreasing. Okay, so that's how you will observe in the log F log L plot. What we want to eventually do is we want to map it to FDLD, right? So we could actually start writing formulas for FDLD for these different lines, and that's one way to do it. But there's a simpler way of doing this. These are, by the way, lines of constant reliability. Lines of constant. Okay, each line will tell you that the reliability is constant, and you can use it for calculations. I'm going to show you a simpler way of, well, not simpler way, but it's simpler for it's probably a little bit complex for us, but simpler for experimentalists, because the experimentalists, if they have to create this line, then they have to run experiments. That each dot means that they have to run for so many million revolutions. So it's very tedious for somebody to experimentally get these lines. So what we're going to do is we're going to use some trick to figure out what these lines will look like, or find the reliability for these lines without actually doing more experiments. And the key idea is that comes from, well, let me see, from here. So what I've shown you here is two lines. Let's say that this line is the line I showed you earlier. This is the log F log L line, which came from 90% reliability. Okay, now we know that the line which will have a reliability of greater than 90% will be the green line. It's going to, we know that for a fact that it's going to be parallel. Okay, this is just an assumption, but this assumption is based on probably experiments to show that it is actually constant. Sorry, it's actually parallel to the orange line. You could have a similar line for less than 90%, just go up, but the calculations will remain the same. So I'll just show it for a line which is greater than 90% reliability. So what you see here is, let's say there's a point A. Okay, this is the catalog rating. This is the rating which you see in the manufacturer spec sheet. This is the rating which shows that 10% of the bearings have failed. If you draw the line parallel to the x-axis, you end up with a point B. Okay, so these 2 points A and B have the same force, same load rating, right? Just based on the way it's drawn. Now, when you're designing a roller bearing for an application, you want to basically design it at a different load, okay, at a different reliability. So this line has a different reliability, let's say 95%. So the green line is 94% reliability, and you want to find what FD is on the 95% reliability line. Okay, but you have no clue how the green line is modeled. You just know that it's parallel to the orange line. So this is a procedure which will tell you how you can compute something about FD, LD, knowing something about the point A and the line, the orange line, which is the line which you used originally for the 90% reliability. So what is done here is the setup is as follows. We are given FD, XD, because that's your ruler bearing application, and you figured out from your application you have a certain load constraint and a life constraint. You also know that the reliability is greater than 90. Okay, our goal is to compute C10. Why do we need C10? Because manufacturers always give you bearings with a 90% success or 10% failure rating. So we want to go from these numbers at a different reliability to C10, which is different from the earlier problem where we only wanted it at 90%. Now we're going at a different reliability. So what is done is, first we can take point B and D. They're always rated by the same expression. So we have FB LB raised to 1 divided by A equals FD LD 1 divided by A. So you can actually write this line for the green line. We have this expression. So here we simplify, write it in some, write a formula for FB. Okay. Next, what we do is we go to the Weibull distribution, which we wrote earlier, and we know that RB is basically our reliability of that green line. It is not 90%. Okay, so we can write the formula for reliability on the 90% or based on the 90% line. So from there we can solve for XB. Remember, the XB is the life of the bearing at reliability not equal to 90%, and solve for XB. Okay, so here in this formula, what we know is RD is known because you specified, because based on your applications, others are just constant. We can specify XB. So finally, what we do is we take this XB, which is the life for not 90% reliability, and substitute in this formula here XB, and solve for C10 rating, which is FB equals C10 or FA equals C10, right? So XB, substitute in this formula, solve for FB. FB is also C10, and we get this. Okay, so this is also C10. Okay, that's it. So in this formula, we are now able to compute what is the C10 rating based on a different reliability. Okay, so this is C10 if you want. So this is giving me the C10 rating at a different reliability. That's all this formula is doing. Okay, let's see how to use this in the next problem. Okay, after this problem, we'll take a break. The design load on a ball bearing is 413 lbf. Okay, so the design load, so this is something which you design for. So it's FD equals 413 lbf. The speed of the shaft is specified as 300 revolutions per minute. It's ND. Is 300 revs per minute. The expected life is 30 kilo hours. So remember the hours, if it's given in hours, it is the subscripted life. So 30 kilo hours, I'll write it as 10 to the 3 hours. At a reliability of 99. So this is our reliability, which is not 90%, it's at 99%. So what we have specs for our application. This is our application, my application, where I desire the bearing to have a very high reliability. 90% is not acceptable. I want to be 99% sure that, or only I can only I only want 1% of the bearing to fail before I replace the bearing. So I demand a higher performance from these bearings. So what is asked is compute the C10 rating. Compute C10 rating uh, on the base of 10 raised to 6. So what it's saying is that we're going to assume that L10 life is a million revolutions. Okay, if it's not given to you what's the L10 life, you just assume it to be a million revolutions. The Weibull parameters are given. So x0 is given, theta minus x0 is given, and b is given. Okay, so this is a straightforward application of the formula where we're given desired at 99% reliability and we are told to find C10. So the formula is, I'm just going to copy the same from here, essentially the same formula. C10 equals FB equals FD times what we had here was numerator x0 plus theta minus x0 natural log 1 divided by RD. I think raised to 1 divided by B, then xt is on top, and then 1 divided by E. Okay, so what we need to do is sub in the values. We have okay, x RD. Okay, RD is known, so this is no big deal. You can substitute it. X0 is given, it's right here. Theta minus x0 is given, it's right here. B is given, B is here. A is 3, could write it here. A is 3, so that's also given. So we're missing, I think, XD and FD, but FD is given. FD is known. FD is known here. So XD is unknown. So XD, we just have to write what XD is. So if you go back, see what XD is right here. XD is LD divided by L10. XD is equal to LD divided by L10. Okay, LD, note the LD is revs, but we're given in hours. So I'll do 60 ND subscripted LD divided by L10. So 60 times ND, 300. LD is 30 times 1000 divided by L10, which is always a million. So XD is 540. Okay, so we have now have okay, so we have 540, which will go straight in here. So you see that everything in this expression except for FB is known. So C10 can be found. So from here we can write C10 equals FP equals 5580 pound force. Okay, this is the answer. And the thing which I want you to note from this calculation is that the interesting thing is, if you look at this load, your application requires only 400-pound force, but at a 99% reliability. In order to achieve that, you have to choose a bearing which can take a load of 5,580 at 90%. And this is a reason why you got such a big load bearing capacity bearing, is because you demand a very high reliability of it. So when you have a high reliability, you will end up with a bearing which can take more weight. Okay, let's continue. So we come to the last case of where these bearings might be design considerations for these bearings. So we talked about radial loads extensively in this chapter so far. So radial loads are loads which are along the radius or perpendicular to the shaft, but you could also have forces which act along the axis of the shaft, right? Now, how do we model the effect of axial loads? What is done is we compute what is known as the equivalent load, which will be some function of axial load and radial load, and use the same formulas as before. So the formulas we used was F times L raised to 1 raised to A, 1 divided by A was a constant. We can actually use the same formula, but we replace this F with an equivalent load. So this gives us a way to capture the axial load without doing big modifications to the to our earlier formula. So what I'm showing here is a graph of equivalent load. So FE, it's a bit small. Let me just rewrite it right here. This thing here is FE divided by V times FR, and on the x-axis is FA divided by V times FR. Okay, V here is a constant. V is a rotation factor, which is equal to 1 if inner ring rotates, equal to 1.2 if outer ring rotates. Okay, so you just get from the conditions of the which one rotates the factor V. But other than that, there's a FA axial load, which you typically know. You know the radial load because you are the designer, you know the radial load. And this is basically a means of obtaining a formula for FE. Okay, why we need FE is because we'll replace the FE in our formula F times L log F log F log F log L curve with FE, and that's the whole idea. So what they found is when they did these experiments on specimens, they found that the ratio is almost a constant till for a factor E, and this I'll tell you what this E is in just a bit. E is just some load factor which I will it's actually non-dimensional number because it's ratio of force to force. It's a non-dimensional number which basically gives us the how the equivalent load changes as a function of the axial load. So it's basically is equal to 1. It's a constant if uh, there is a condition which I'll show you, which you can use to compute E. If E is that condition is less than E, and if it is greater than E, then it actually follows a line with a slope, and that slope is something which will come from a table. Okay, so our goal is to figure out what this E is. If you know this E, then we can basically figure out which side of which line basically describes the equivalent load. Is it the constant line or it's the line with the slope? Okay, so let's elaborate a little bit more about uh, this formula. We'll actually divide into two regions. This is region 1 and this is region 2. Okay. In region 1, what you see is that, and this is too small, so I'm just going to rewrite it. Let me just rewrite this as Fe divided by V times Fr, and this is Fa divided by V times Fr. Okay, so region 1, Fa divided by V times Fr, right? This is E depends on the values on the x-axis, so Fa divided by V times Fr. If this ratio is less than E, and I'll tell you how to compute E, just bear for a moment, then your model is basically a straight line. Model is 1. So it is Fe divided by V times Fr equal to 1, right? It's just this line. This line is this. That's what I wrote down. But if you are in this region, so region 2, what you'll do is you'll check for Fa divided by VFR, this ratio. If it is greater than E, as you can see here, this part, then we'll basically use this model, right? This model is going to be written down as, it's basically a line with equation y equals mx plus c. What is y? Y is basically Fe divided by VFR equals x. X is Fa divided by VFR. Okay. This is m x plus c. Now it turns out that this m will actually, it comes from a different table, and I'll show that in a bit. This m is basically going to be uh, interpreted as y. So this is just another constant, write as y. And this constant here is going to be x. Okay, and this x and c will come from a table. So y, x, there's a table which gives you y and x. So all I'm saying is that once you've determined its line number 2, you can pull up y and x from a table and then compute the relation between Fe and Fa. Okay? And once you get that relationship, you can then figure out what Fe is, because Fa and Fr is known. Okay? So what I can do is I can rewrite this second formula as Fe equals yi Fa plus xi v times Fr, right? I'm just moving VFR on the other side. This is the formula. So you can basically use this formula to compute what Fe is, given Fa, Fr, V, and Xi, Yi come from a table. So Xi from a table. I'm just going to show you the table quickly, and then you will actually, we'll actually solve a problem. So it will become super clear how to actually use this table and solve problems. So this is the table I was talking about. Okay, so we have, in this table, we have E. This is right here. We have this formula. This is basically saying if VA divided by VFR is less than E, which is basically our model 1, then you'll use this Xi VI, right? Remember, Xi VI sits in front of this. So Xi is, I think, Xi is 1, Y is 0. Oh, did I switch it? Xi is 1, Y is 0. So it's just going to depend on VFR. If not, if it is in region 2, which is, you'll check this ratio is greater than E. if then you'll use this region and then you'll use x2, y2 from this part of the table. Okay, so the formula is, as I said, I'm just going to rewrite this formula, the same thing I wrote here. It is Fe equals, I'm just going to write it in such a way that though I wrote x later on, I'm going to write it first. So I wrote x, y first, x second, but I'm going to switch this up so that way it is easier for you to use the formula. So I'm going to write it as xi v fr plus yi fa. And the reason why I'm doing that is because when you use the formula, you shouldn't switch them. If you switch them, you'll get the wrong answer. So it's best for you to use this formula, because when you read this formula, you will see that xi comes first, x1 comes first, x2 comes first, and then a yi comes second. And so you will not make a mistake. So you just substitute x1, y1 depending on which region you are, 1 and 2, and then you're all set. Okay. Now it turns out there's something else we need to compute E. Okay, how do we compute E? E is just sitting there. We'll actually use this formula to compute E. We'll have to compute Fa divided by C0. Fa is the actual load given to you. C0 is the static load. It will be something given to you. Once you know this formula, once you get this, you can compute E. So if you get, for example, 0.021, then you'll say E is 0.21, and then you will use that E to figure out which region it lies in, and then use model 1, model 2. Now I said that very quickly, but once I solve a problem, I think this will become very clear to you how to actually use this table and all the things we talked about. So I'm going to just summarize how we're going to go about solving a problem with equivalent load, and then just apply that to a problem. And I think that will make it super clear how to do this. So here is a summary for the bearing selection so far. So first, design determines FA, FR, C0. So you have a bearing problem for a particular application. You are going to figure out how much radial, how much axial, and how much static load is going to be taken by the bearing. So you do that. Second step, we'll compute FA0 by C0. Okay, you know FA, you know C0, you can compute that. Okay, now with that in mind, once you get this, we will go ahead and look at table, I'll call it table 11.1, and we'll compute the corresponding E. Then compute E using table 11.1. I just showed you, right? Next step is, once we determine E, so once we know what E is, we can then use these checks. We can use this values less than E or greater than E to figure out which constants or which model to use. So the next step is use Fe equals xi v fr plus yi fa, and table 11.1 to compute xi yi. Okay, once you get xi yi, you can compute Fe, and we were really after Fe. That is the whole point of the exercise, is to compute Fe, because once we get Fe, now we can use now use Fe in this equation. Fe is a constant. Note that Fe earlier was only radial load. For the calculations we talked about, we are going to now use Fe in place of L, because this is the equivalent load. Okay, question. Yeah, so you can use MATLAB for any homework problems. It's absolutely fine. You can also use MATLAB if you want for the project. In the exam, of course, you won't have access to any of this. So you might want to also do these calculations by hand so that you understand what to do. But for homework, you're more than welcome to use any software tool you want. Okay, so that answers the question in the chat. Okay, so what we'll do is, and this is the last thing in this before we wind up, is we're going to use this recipe in order to figure out how to compute the life, okay, when there is an axial load. So here is an example problem. Uh, an angular contact ball bearing has an axial load Fa, 400-pound force, and a radial force of 500-pound force. Okay, applied with the outer ring stationary. So if the outer ring is stationary, then I think V equals, is it, see, outer ring stationary. I think that's right here. Outer ring stationary. So if outer ring stationary, then inner ring rotates. So V equals 1. Okay, outer ring stationary. The basic static loading rating is C0 is 4450 pound force, and the basic load rating, so C10 rating, is 7900 pound force. Estimate the L10 life and at a speed of, okay, so it's asked to compute the R's L10 life in R's, so that would be, I believe, the subscripted L10. Speed is, you can call it N10, 720 rev per minute. Okay. Okay, so what's asked is to compute the uh, L10 life. So L10 life is 60 N10 subscripted L10. Okay, so this is L10 is unknown. Okay, however, N10 is known, that's given to us. And obviously, um, L subscripted L10 is on L10 is also unknown. But because we know this relationship, that is the F E, remember that we cannot use the FL formula as it is because there's an axial load. So we need to replace F with an equivalent load. So FE LE 1 divided by A equals C10 L10 1 divided by A. Okay, so in this case, let's see. So we don't know FE, LE, do we know LE? L10 is not known, but we're going to assume in this case that the L, this is a million revolutions. So we want um, the the application to take up to a million revolutions. So we'll assume that. So C10 is known. C10 is given here. So C10 is known. So what we're trying to do here is effectively, so here's what we'll do. Why is this happening? Okay. First, compute FE using table 11.1, right? That's we can do because we know everything about FA, FR, and so on. And remember our summary, this summary said, if you know FA, FR, C0, you can actually compute FE. This lays down the procedure to compute FE. So that's what we'll do first. Okay. The second step is once we get FE, then we can compute we are going to compute L10. This is unknown. This is unknown. But if we substitute this inside this, it goes here, then we can write an expression which we will have only Fe, Le, which is known, C10 and L10, substituted by L10, and we can compute L10. So we can compute L10 given Fe, right? So the second step is uh, compute L10 given Fe from, let's call this asterisk. Essentially, we'll substitute the green, the pink item, and then we'll left with the formula for L10. So this is my strategy. I'm going to first compute Fe using this table and this whole algorithm, and then we can compute L10 very easily. The second step is the easier one. First one is going to be a bit of involved. Okay, let's get to solving Fe. Step compute Fe from table 11.1. Okay. Okay, so let's get to this. What does it say? Design determines this. This is known. Compute Fa divided by C0. So step 2. Fa divided by C0 is Fa is 400, C0 is 4450. Okay, so it comes out to be approximately 0.09. Okay. Okay, now next step is then compute E using table 11.1. Okay, so if you look at table, we are looking at 0.09. So it looks like it's somewhere here. 0.084, 0.11, 0.28, so it looks like I need to use this part. I'm just going to rewrite this. So from table 11.1, I'm going to just rewrite this 0.084, 0.11, 0.28. Okay, so what we want here is for what, so at 0.09, we want to figure out what is this E. Okay, now one way to do this is to draw to linear interpolation, like 0.9 lies in between this, and you can find exact value to the last decimal. But here I'm going to just make a guess that this looks like it's equally spaced between, so 0.9 lies approximately in between these two. So probably we want to find a value. So I would just guess it's 0.29. It's probably a little bit less than 0.29 because this seems like it's closer to 0.09 is closer to 0.084 than it is to 0.11. So it's probably less than 0.29, but I don't think it's a it'll have a big effect. So better guess by using linear interpolation. Okay, but here it's not needed. Okay, I will do a linear interpolation eventually, as you see, but for this it's not needed. So we have what we needed, which is E. Our E is at 0.09 is 0.29. So that is what we were after, and that completes step number 2. Okay. Now we go to step 3. We want to compute Fe using this formula. Okay, so let's get to that. Okay, so here what we are after is we have 0.09 and we have to deal with these models, right? Remember, there were two models, the model 1, model 2, and these models depends on the value of, we want to compute Fa divided by VFR and compare with E. If it is less than E, we use model 1. If it is greater than E, we use model 2. So let's figure that out. So FA divided by VFR. So FA is 400, FR is 500. 400 divided by 500 is 0.8. Okay. So then we say go back here. We have to compare it against E. So we see that FA divided by VFR is 0.8. It seems to be greater than 0.29, right? This is greater than E. What is E? E is 0.29. E was computed right here. Okay, so what does that mean? Well, if you go to this table, it says that if this is greater, then we need to use model 2 because V divided by FA divided by VFR is greater than E. So we say use model 2 or other model 2 where we look at, essentially now we have to look at this part of the table. Okay. This is because model 2 requires x2, y2 and not x1, y1. So I'm going to rewrite this entire thing here, this, and this, so we can go from there. So we have, let's write a new page from E. I had already written this down, 084, 011, 0.28, 0.3. Okay, then I have to write x2, y2. So x2, y2 is 0.56, 1.55, 1.455, 1.45, 0.56, 0.56, 1.55, 1.45. So this is the table. Okay, now what I'm trying to do is I'm trying to estimate, in this case, my goal is to estimate, as you can see here, what is the value at 0.09. So I'm going to write let me write in a different color, 0.09. Okay, so I estimated this to be 0.29. Now I'm just going to get the same values for this. It's clear that if you want to find what happens at 0.09, if it's 0.56, 0.56, it just means that it's still 0.56. It's this value which I think I want to do a little bit more better job. I could just, if I want to find a value in between based on these, I could guess this to be 1.5, which is valid because it looks like it's halfway, but I want to do a better job than this. I'll not I will use linear interpolation. So what I'll do is I'll assume, so we are doing the second region, right? This region, model 2. I know the value is on the x-axis. If you see this table, it is FA divided by VFR, and y-axis FE divided by VFR. So we have, we're going to interpolate as a function of this. So 0.084, 0.11, and here we have sitting at 0.084 is 1.55. Well, actually, the other way, 0.084 is, this is this interpolation is not anyway related to this line, by the way. These two are different things. I sort of confused you by showing this, but this is not related to this. This is a different interpolation, not really shown here. It's actually buried inside this table. We're trying to interpolate this first column as a function of the last column. Okay, so we're just trying to find relation. So I shouldn't have shown it that way. This is FA divided by C0, and then the this is y2. I'm trying to interpolate y2 as a function of FA divided by C0. That's all I'm trying to do. seems like the line is like this way, because this coordinate okay, because this line seems like 1.55, and then this line is down there 1.45. Okay, and then I'm interested in figuring out what the value is at 0.09, is this. So this is my unknown y2, let me call it y2 star. So all I do is I do linear interpolation. So for linear interpolation, I just use, this is giving me problems. Okay. So y2 star minus, you can take any point. So let's take 1.55 divided by 0.09 minus the corresponding point. So I'm just trying to fit the straight line, the green line. Then you can do 0.11 minus 0.084 divided by 1.45, because 1.45 corresponds to 0.11 minus 1.55. Hmm. Right, 1.55. Okay, so we can solve for y2 from this. Comes out to be 1.527. So we guessed it to be what? 1.5, remember, because based on this, it's actually a little bit closer towards this one, as you can see, because 0.09 is closer to 0.084 than 0.19. So I could write here from this value 1.527. So this came from here. Okay, linear interpolation. Okay, so with that, we are now ready to find F equivalent, because let's go back to the summary. We have to use this formula, right, where x I yi would be x2 y2. So let's just use that. So Fe equals, since we're using model 2, model 2, we can write Fe equals x2 v fr plus y2 fa. Fe equals x2 was 0.56, right, just this, and 1.527 for that. 0.56, v is 1, fr is given to us, it's 500, y2 is 1.527, fa is 400. Equivalent load from this comes out to be 890.8 lbf. This is what we were after. This is step one. We've computed from this problem. We said first we want to compute Fe. We have now computed Fe. Next, we'll use these formulas to compute L10, subscripted L10 given Fe. Let's do this. So next, compute L10. Okay, so Fe, sorry, this is not right. It's Fe Le 1 divided by A equals F, or rather F C10 times L10 1 divided by A. So Fe Le, I'm just going to substitute 60 N10 L10. Right? This is something which I had written down as two formulas. I just combined it, and now I can substitute 890.8. Le is a million. This is 3 equals C10 7900 60 times 720, it's given L10, subscript L10 is unknown, 3. So one equation, one unknown, we can solve for L10. This will be an answer which will come in hours. It is a huge number, 16145.7 hours, okay, which is not very illustrative. So we can convert this to divided by 24 to convert in days, 6.72 days. And then that also is maybe less intuitive to some people, so we'll try to convert that to years. So what this is saying, this calculation is showing, is that the L10 life, that is the 90% reliability life, is 1.84 years. So come for 2 years. After 2 years, you have to replace it. Maybe that's bad, maybe that's good, depends on your application.